Okay, so in this little video, I kind of want to try as best I can to illustrate using kind of like intuition about some basic concepts from probability, why we expect the Bernstein polynomials to uniformly approximate the sort of the given function f. Okay, so I'm going to recall the definition of the Bernstein polynomials, right? Dang it. So Bn f of x is defined as sum from k equals 0 to n of f of k over n times the binomial coefficient n choose k, x to the k, 1 minus x to the n minus k. So if you've seen any of this stuff before, you might recognize this as the probability of k successes in n coin flips where the coin has probability, or maybe instead of successes, let's call them heads. K heads, probability x of being heads, right? The reason for that is that, if you write down a specific string of like heads and tails, let's say you write down n, like n characters, each one is like a heads or a tail, n results, each one is a heads or tails, then the probability of that specific string happening is going to be, x to however many heads there are times 1 minus x to however many tails there are, right? But then if you're just interested in the total number of heads out of all of the coin flips, then you would want to sort of add up all of those probabilities over all of the ways that there could be a specific number of heads. So if we say, okay, there's going to be k heads, then ask like how many ways are there for there to be k heads? There's going to be n choose k ways for there to be k heads, right? And if the probability of the heads is always x, then and tails is always 1 minus x, then this is always the probability for each one of those strings. So the total probability of there being k heads is just this: n choose k times x to the k times 1 minus x to the n minus k, right? Or if you want to say like k, let's actually do it like this way. So k ones, and coin, you can think of it as a coin flip, but now we consider heads to be the number 1 and tails is 0, right? So there's sort of these binary trials. Or in another, so, okay, yeah. Or alternatively, the probability that the number of ones over n equals k over n, right? I mean, you can just divide this all by n, obviously, and it doesn't affect the probability. But here you can think of this as like the average success rate or something, right? So what we're kind of doing is, we see k over n in here, and f is like this function. So you can think of f as basically this function of a random variable, which is the average, of basically the result of n like coin tosses. Yeah, it's the average of the result of n coin tosses, right? So say, x is the variable, a random variable x1 plus x2 plus xn, where each xj are, the xj are independent, xj are independent coin tosses with probability x of 1 over n. If this is our variable, then Bn f of x is actually the expected value of f of x. Okay, where this x is this random variable, because what we're doing is we're adding up the values of f evaluated at whatever outcome value of x we are looking at times the probability of that outcome, right? So the probability that x equals k over n is precisely given by this, okay? So this is the expected value of this f. And now, so here's the kind of, weird thing, or not weird, but maybe a little bit advanced, which is that if we think of this x as this big average, when n grows very, very large, there are theories, there are sort of, or theorems from probability theory that let us approximate this. And you can actually approximate the probability distribution over the possible values of x by a continuous function. So like what I'm saying is, okay, so say we define p on like a function p on the set, k over n, or call it pn, sorry, k over n, where k equals 0, 1, n. So p just takes values specifically on the set of k over n, right? So it's just a finite set. And define it by p of k over n is, and choose k, x to the k, 1 minus x to the n minus k. So pn is the probability distribution of x, okay? So where x is this, average of these independent coin toss variables, okay? So then for large n, Pn can be approximated very closely by the continuous probability distribution, probability density, let's say. And I'm going to define it like this: Pn tilde of y equals, and this is where it's kind of weird. So basically, it's a normal distribution, 2 pi sigma squared e to the negative y minus x squared over sigma squared, where sigma equals the square root of x 1 minus x over n. Okay, so a few things to unpack here. Okay, so first of all, what's x doing in here, right? Remember, x is something that we kind of fixed at the beginning. Okay, so we fixed x. Okay, so we are imagining x fixed for now. Now, if the probability of success of this coin toss, if the probability that it gives a 1 is x, and the probability that it gives a 0 is 1 minus x, then the average, right, like the expected value of a single coin toss is just x, right? The expected value of a single coin toss is just x. So it makes sense that the mean of this normal distribution here is going to be x as well, right? Or the expected value of the average here is also x, basically, is also little x, right? So the expected value of little x is, or the expected value of big X, the random variable, is little x for this given little x, okay? So this big X random variable, it's a sum of variables that all depend on like the parameter little x, but we're considering it constant for now, okay? So so the expected value is little x. So that's kind of why we use little x as the mean of this Gaussian here. And then this is sort of, so this is just like something that I'm going to ask you to like take on faith for now, basically, but that this is a very good approximation of this density function when, or of this probability mass function, this is a very good continuous approximation when n is very large. And as long as x is not too close to 0 or 1. So we're gonna kind of like sweep this under the rug for now. Okay, so just imagine that basically all the, everything is sort of being cooperative right now. So x is not super close to 0 or 1, and n is like super large. Okay, then this becomes very close to this. All right. So and you can see how like this gets really this is badly behaved if x gets super small, because then this gets like really small, so the function growth like has a huge peak, and then this is also really small, so it gets super sharp. So it's kind of it's weird. But we're just going to pretend that x is not particularly close to 0 or 1, and this is a very good approximation. Then we can approximate Bn f of x very closely by the integral from 0 to 1 of f of y p n of y dy, because this is the continuous expected value of a variable with density, probability density function. So if the probability density is p tilde, pn tilde, then this is the expected value of f of y. Sorry, so of f of f of a variable like this. Okay, so this is the expected value for the continuous version, and so this is basically, you can kind of think of Bn f of x as being like this, essentially. When n is very large, this, and x is not super close to 0 or 1, this is a very good approximation. Now, so what I want to do is, let's think about Pn tilde of y, okay? It's like a Gaussian, right? It's a bell curve. And notice that sigma is proportional, if you think of x as being a constant, right? Sigma is proportional to 1 over the square root of n. So as n grows, sigma gets very small. So even if x is not super close to 0 or 1, this, as n gets large, this peak gets super sharp. Okay, so let's draw a little sketch here. I'm gonna make a little cut while I draw the picture. All right, yeah. So you can see in this picture, here's Pn tilde of y, and it's just, and so it's, hopefully it's not too confusing that y, actually right now y is like the x-axis, but it's because we already used x. X is like a constant, remember. So we're just using y as like another variable that could be like the input, okay, the input of a function. So this is like the y-axis down here, and Pn tilde of y is graphed, okay, and it's just a Gaussian. And as you can see, since sigma is like the standard deviation, right? Sigma is proportional to like 1 over square root of n. So as n gets large, sigma gets very small. So this number, the constant out front here, gets very large, meaning the peak gets really tall. And this number also gets very small, meaning that like y only has to be a little, like y can be very close to x, and this number will still be big. So the overall number will be like really, so it decreases very fast as y moves away from x if sigma is small, right? So so basically that's like the width of this peak is basically like proportional to 1 over square root of n, as is like the height of the peak. Okay. So, or sorry, the height of the peak is proportional to like square root of n, I guess, roughly, something like that. So the height of the peak goes up as like square root of n, and the width goes down as like 1 over square root of n. So basically what happens is that the total amount of like probability that's concentrated, the area that's concentrated in this curve close to x gets like very, very close to 1. In fact, so like so let's say this was like x minus delta, and this is like x plus delta for some delta, okay? As n, if you fix some delta, as n gets very, very large, almost all of the area under this curve is going to be just in this tiny interval here, okay? So what this means is basically like, if you think about this integral, right, where you multiply all the stuff by f of y, if Pn tilde of y, as n gets very, very large, f just doesn't change, obviously, right? So f is just sitting there, but as n gets really, really large, this is getting super focused around x, right? So what's happening is like Pn tilde sort of picks out the values of f right around x, and those contribute a decent amount to the overall value of the integral. And then since Pn tilde is super small when you get far away from x, right? So this is very small when y is not close to x, right? Then like, no, it doesn't really matter what f is doing outside of this tiny interval right around x, because Pn tilde gets like extremely small out there, right? So here's kind of how you can, so like intuitively, right, we expect that Bn f of x will approach f of x itself, right? Because if this is just getting super narrow and focused around x, then the only value that ends up mattering here is f of x. And then basically what you're doing is roughly, you know, forming this extremely tall spike whose total area is like 1, and then multiplying that by like f of x. So the total area would just be f of x after that, right? So so this is going to sort of approach f of x. And so the way we can, it is going to approach f of x, right? And so the way we can kind of like estimate, so what we want to do is kind of estimate the error, basically, right? So how do we pick n uniformly so that the error between Bn f of x and f of x is small? Okay, so first of all, I'm glossing over a few things. So first of all, this is actually, I was kind of lying a little bit when I said this is the expected value, because technically Pn, so technically Pn tilde is also, it is defined for all y in R. So technically this curve extends all the way out. So just the piece, like if we just integrate from 0 to 1, that's not genuinely the expected value here, because that's leaving out some of the pieces of the domain of Pn tilde. But for large n, almost all the probability is concentrated in 0, 1, the interval. So basically, like what I'm saying is that, you know, in the background, part of our approximation is actually just picking n to be large enough such that like the error between this and the actual expected value is, or like the error, like the amount of Pn tilde that we're leaving outside of the interval 0, 1 is extremely small, basically. That's part of it in the background, but I'm not going to really, let's just sort of ignore that. Okay, so let's pretend that this is genuinely the expected value. So basically what I'm saying is like, let's pretend that the integral from 0 to 1 of Pn of y dy is equal to 1. Okay, even though it's actually, so it's actually less than 1. But by picking n extremely large, we can get it very, very close to 1 is what I'm saying. Okay, then imagine, so what we can do, okay, actually, before I do this, so let's examine the error, right? So f of x minus Bn f of x, what we're saying is that this is approximately, for large n, this is approximately the difference between two integrals. Okay, so so this is approximately the difference between the integral from 0 to 1 of f of x p n tilde of y dy minus the integral from 0 to 1 of f of y p n tilde of y dy. Okay, and the reason for this, right, is what we were saying. Well, so first of all, like this integral, if we pretend that the integral from 0 to 1 of pn tilde of y dy is 1, then f of x is just a constant in this integral. So this would literally equal f of x under this assumption, right? Of course, it's slightly less than f of x, but again, like I said, when you pick n extremely large, this gets very, very close to 1, so this gets extremely close to f of x, okay? So that's just one thing sort of floating around in the background. And then over here, the reason that this, this is close to bn f of x by exactly what I was just saying before, right? What I'm saying is that bn f of x is very closely approximated by this integral from 0 to 1 f of y pn tilde of y. And that's because, remember, this is the distribution for the binomial. Like this is the binomial distribution that bn f of x is like defined as like the expected value of f of this average variable with the binomial distribution, right? And then when n is very, very large, what I'm saying is that that's very closely approximated by a continuous version of the same expected value, okay? So that's why this is basically, what we get. This is the approximation of bn f of x, okay? So the idea is that, okay, this integral, almost all of the value of this integral comes from a piece right around y equals x. So like the integral, so if you split these integrals up into, so what I'm going to do is split them up, okay? So we'll have like the integral from 0 to, and I'm going to sort of combine the, so, you can combine these two right now to get the integral of from 0 to 1 of f of x minus f of y times pn tilde of y. And then I'm going to split that up into different regions, okay? So I have the integral from 0 to x minus delta of f of x minus f of y pn tilde of y dy plus the integral from x minus delta to x plus delta of f of x minus f of y pn tilde of y dy plus the integral from x plus delta to 1 of f of x minus f of y pn tilde of y dy. Okay, so I combined these two integrals together first and left it as an integral from 0 to 1, and then I split it up into 3 regions, okay? So you see it's the same thing inside in all 3 of them, but I split the interval, right, up into like basically these 3 regions. So there are 3 regions. And the point is that so what we can do is like, since as n goes to infinity, the probability mass of pn tilde of y gets concentrated in x minus delta, x plus delta, we can pick n large enough that the sum of the integrals from 0 to x minus delta of pn tilde of y dy plus the integral from 0 to, it's not from 0, so from x plus delta to 1 of pn tilde of y dy is less than any epsilon greater than 0 we want. So, So actually, let's call this like epsilon 1. So epsilon 1 for any epsilon 1 greater than 0. Okay. So basically what we're doing, right, is we're thinking about like how can we control. So remember, the reason I split it up like this, okay, is because, like I said, I expect almost all of the value of this integral, right? This integral I'm saying is supposed to get very close to bn f of, or to f of x itself, right? So I'm saying this integral is supposed to be extremely close to f of x, and almost all of the value of f of x that you're getting in this integral is coming from this tiny interval here. So all I have to do is basically control the error from the other parts of the interval that we're integrating over by just forcing Pn to be extremely small in those regions. And then in this interval here, I just have to make this interval small enough that f itself is like almost constant on that interval. And then we have an area that's like almost equal to 1. So that basically the integral just over this piece is almost exactly f of x itself, okay? So what I'm doing, that's why I split up in this expression. That's why I split it up into 3 pieces, because I'm saying this piece we control differently by forcing f to be close to being constant, and then Pn, like making it so that like n is big enough that the integral over this region of just Pn tilde of y is almost 1. If you think of this f of x minus f of y as being like very close to 0, then that makes this this integral very small. Out here, we can't force f of x minus f of y to be close to 0 because y is not actually close to x, right? In these, y itself is not close to x in this integral or in this integral, because y is only staying outside the interval from x minus delta to x plus delta in these 2 integrals. So the point is that I'm forcing these to be small by making it so that like Pn tilde itself is very, very small for these integrals, okay? And that the total integral of Pn tilde over here on both of these intervals is like very small, okay? So say n is large enough for this to hold, right? Then the absolute value of the integral from 0 to x minus delta of Pn, or sorry, of f of x minus f of y, Pn tilde y dy plus the integral from x plus delta to 1 of f of x minus f of y, Pn tilde of y dy is less than or equal to the integral from 0 to x minus delta of the absolute value of f of x minus f of y, Pn tilde of y dy plus the integral from x plus delta to 1 of absolute value of f of x minus f of y, Pn tilde of y dy. And then basically, so we can't force f of x minus f of y to be small. That's what I'm saying. But what we can do is bound it above by a constant, right? And then, so now say m is an upper bound of f, absolute value of f on 0, 1, right? This has to exist because f is continuous. So if f is continuous on a closed interval, it's automatically bounded. So let's just say m is any upper bound, okay? M is an upper bound on absolute value of f. Then absolute value of f of x minus f of y is less than or equal to 2m, or let's say less, yeah, like less than or equal to, it doesn't matter, right? For all x and y in 0, 1. So if we call this whole thing, call this star. So star is less than or equal to the integral from 0 to x minus delta of 2m Pn tilde y dy plus the integral from x plus delta to 1 of 2m Pn tilde of y. dy, which is then in turn, if you factor out 2m, right? So this is 2m times the integral from 0 to x minus delta pn tilde y dy plus the integral from x plus delta to 1 of pn tilde y dy. This is now less than 2m epsilon 1, right? Because we showed that, or we picked n to be large enough that these two integrals sum to be less than epsilon 1, okay? Okay, so that's how you can control those two terms. And then all we're left with is this middle term. How do we get this to be small, right? Well, that's where the uniform continuity of f comes in. So you can pick delta. Basically, now we have to like pick delta to make this interval be so small. So the idea is like, it's actually kind of, we did it kind of backwards. Like we should really be picking delta first to make this be very small, and then picking n large enough so that like this is true. So this is kind of like, we're doing this after we pick delta, okay? But so if we pick delta such that like absolute value of f of x minus f of y is less than epsilon 2 for x minus y less than delta on 0, 1, then what? So then that means that the integral from x minus delta to x plus delta of, well, the absolute value, let's say, yeah, the absolute value of this integral of f of x minus f of y, pn tilde y dy is less than or equal to, so we can do the triangle inequality for integrals, so x minus delta, x plus delta of absolute value of f of x minus f of y, pn tilde y dy, and then this is less than or equal to the integral from x minus delta, x plus delta of just epsilon 2 pn tilde y dy, which then is less than epsilon 2 since the integral from x minus delta to x plus delta pn tilde y dy is less than 1, right? And this is just less than 1 because pn tilde is supposed to be a probability distribution, okay? So in all, if we pick delta this way and then pick n large enough for delta, we have that bn, or sorry, that f of x minus bn f of x is approximately this whole thing. So is approximately, you know, the integral from, so let's see, what did I do? Right, it's approximately this whole sum here. So let's call this star star, okay? So this is approximately, oops. Approximately star star, which then is less than or equal to, by the triangle inequality, right? If we apply the triangle inequality of this, we just get 3 integrals, right? So less than or equal to the integral, well, actually we can do the sum, like, okay. So we have the 0 to x minus delta, and I'm just gonna put dot 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 in here because it's the same thing in each one, plus the integral from x plus delta to 1, dot dot dot, plus the integral from x minus delta to x plus delta of dot dot dot. Oops. So this is less than 2m epsilon 1, and this one is less than epsilon 2, right? So pick, epsilon 1 and epsilon 2 such that 2m epsilon 1 plus epsilon 2 is less than epsilon. If you're given, right? So this is kind of an outline of how you might pick capital N to show that like Bn f of x is close to f of x, right? The outline is like this. Given epsilon, first, pick a delta so that, so pick epsilon 2 to be like epsilon over 2, right? Say epsilon 1 can be like epsilon over, it doesn't have to be less than, it can be equal. So epsilon over like 2m, and then over actually 4m, right? And then epsilon 2 can be like epsilon over 2. So given epsilon, pick delta over here, right? Pick delta such that absolute value of f of x minus f of y is less than epsilon over 2, right? For absolute value of x minus y less than delta. Then once you have that delta, pick capital N so that the total area, pick capital N, right? So that the total area here is less than epsilon 1, where epsilon 1 is now epsilon over 4 capital M, right? So if you pick capital N that way, then all of this stuff should work out. And this, of course, there's this approximation, which I'm not really going to deal with. But again, those are just some extra conditions that you can kind of like work out not without a whole lot of difficulty, that just make you pick capital N to be like the maximum of several different things. But this is kind of the important thing, I think. So this is hopefully, I mean, I know it's complicated. It's very complicated, but this, I would say, is kind of like, to me, I think it's possibly the most intuitive way of thinking about why the BNF functions basically uniformly approximate. The only thing we also haven't dealt with is like, early on, we made this assumption that x is not too close to 0 or 1, but then you can kind of deal with that separately. You could deal with that separately by basically invoking like continuity of BNF and saying that, like, because basically as n gets very large, the approximation works. So actually, let me like, yeah. So about x not too close to 0 or 1. For n very, like, as n grows, the approximation of Pn by Pn tilde, right? This was remember, this is the discrete version. And this is the continuous, so the normal distribution is acceptable for values of x closer and closer to 0 and 1. So basically, the sort of margins where like x is not allowed to be close to 0 or 1, those also shrink, and they shrink approximately as like 1 over square root of n, I think. Those shrink as you get close, as n gets larger and larger. So basically, you can also pick n to be large enough that that this approximation works for almost all the values of x in the interval. And then if you want to deal with the values of x right at the endpoints, like right near the endpoints, you can sort of deal with those separately by invoking something about, like, I don't know, continuity, or, who knows? I mean, there's other ways of dealing with it, but that's like kind of another technicality. I think that the real like spirit of the proof that they give in the book is contained in all of the stuff I just did, where we kind of assume that x is not super close to 0 or 1 relative to 1 over square root of n, and then also that n is large enough that this continuous approximation works and all of that stuff. Okay. So anyway, it's okay if you didn't really follow a lot of this, especially because I know a lot of you probably don't know a ton about probability. That's fine. Again, please don't be discouraged. Okay. In the next video or two, I'm going to reel this back in, and we're going to go back to looking at, like, instead of all this continuous stuff, all these continuous variables and stuff, we're just, and no probability, we're just going to go back to looking at the actual functions as they are defined in the book, the Bernstein polynomials, and I'm actually going to do some estimation with those directly to show you how this picture actually plays out in that setting. Okay? All right.